Hi. Today I'd like to go over linear programming. So you have an investigation to work on, and I want to kind of go through it with you. Since I can't be here with you, I'll do it virtually. So in this problem, it says that you want to make two kinds of paint, spring green and flash green. And it takes yellow tint and green tint to make these paints. And it takes different amounts of the yellow tint and the green tint. And you want to make as many gallons of paint as possible. So we're trying to maximize our gallons of paint here. So the very first thing I want to do is define my variables, and I'm just going to use our old standard x and y. So x is the gallons of spring green, y is the gallons of flash green. And at this point, I need to write a system of inequalities to show the constraints on the system. So my constraints here, first off, let's jump to the easy one. I can't have negative gallons of paint. So x has to be greater than or equal to 0. Y has to be greater than or equal to 0. I know it's trivial, but we do need to include those. Then let's look at the limit of yellow tint. So we have a total of 32 units of yellow. And to make paint, I need 4 units of yellow for every gallon of spring green. So 4 times however many gallons of spring green I make, that's how many units of yellow tint I'm using. In addition, I need 1 unit of yellow tint for every gallon of flash green. And that is limited to being less than or equal to 32 total units. By the same token, with the green tint, it takes 1 unit of green tint for every gallon of spring green, and it takes 6 units for every gallon of flash green. And that is limited to being less than or equal to 54 units. So these 4 equations, those are my constraints. Now I need to graph these inequalities. Well, the first 2 that we did are very easy. That's just the x-axis and the y-axis. So I have those constraints. And now let's graph the other 2. And instead of making each of these be worth 2 units, let's make them each be worth 1. And I think you can see that if, let's do the first one up here, if x is 0, y would have to be 32. If y is 0, x has to be 8. So let's use that. 1, 2, 3, 4, 5, 6, 7, 8. And this equation has a slope of -4. So it's up 4, 1, 2, 3, 4, and over 1, up 4, over 1, over 1, and so on. So this I get, it's not the greatest straight line, but that should be a straight line there. For the other equation, x plus 6y, if x is 0, y would be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And it has a slope of -1/6. So 1, 2, 3, 4, 5, 6, down 1, 3, 4, 5, 6, and down 1. And this one is going like that. So I now have my constraints graphed. And this region right here, and anything inside of there, is what we call the feasible region. So any point along the borders or inside of the borders is a feasible number of gallons of spring green and flash green that I can make. And I'm looking to maximize the number of gallons. So it says here, write an equation to use to determine the best result. That is, write a function of x and y to be maximized or minimized. And since we are trying to maximize gallons of paint, we're looking at gallons of spring green plus gallons of flash green, and I want that to be a max. So my function of x and y in this case is just x plus y. Now, as I said in class, according to the theory of linear programming, the best result will always occur at a vertice. So, here, 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 or here. That's where we will make either the most or the least, and we are trying to make the most here. So, we make a table of x, y, and f of xy, and we put in our vertices. So one vertex, x is 0, y is 9, which gives me f of xy equal to 9. Another vertex is at 8, 0. That gives me 8. A third vertex is at 6, 8, which gives me 14. And finally, we have the origin, 0, 0, which gives me 0 gallons. So, I make my most gallons of paint when I make 6 gallons of spring green and 8 gallons of flash green. I hope that that little explanation helps you with how to do linear programming.